Hello once again. Welcome back to our Chem 152 video series. In this video, we'll be talking about freezing point depression. This question says that we have an aqueous salt solution that is 15% in KCl. We are also given the freezing point constant for water and the regular freezing point of water, and now we are meant to find the freezing point of the solution. Now, to find the freezing point of the solution, we'll need to use this equation. The freezing point, represented by TF, is equal to I multiplied by KF multiplied by lowercase m. We'll go through what each of these terms mean. To find the freezing point of a solution, we'll start by writing T of the solution is equal to the freezing temperature of the solvent minus I times Kf times lowercase m. Let's hit pause for a moment and go through what each of these symbols means. T solution is the freezing point of the solution. In the third line of the question, it's asked us to find that. We'll box that in and remind ourselves this is the final objective of the problem, to find the freezing temperature of the solution. We'll say equals, and now temperature of solvent stands for the freezing point of just the solvent. The letter I stands for something called the Van't Hoff factor. For the purposes of Chem 152, we can think of the Van't Hoff factor as the number of ions that the solute breaks into. This will depend on the solute that we're studying. Not every solute will break into ions. Solutes that don't break into ions are called non-electrolytes. If this is the case, we assign a Van't Hoff factor of 1.0. Now, for solutes that are completely soluble or are considered strong electrolytes, they will break into pieces. A strong electrolyte will break into at least 2 pieces. For some electrolytes, we could have more. We also have weak electrolytes that are slightly soluble and only break a little bit. Weak electrolytes will have a Van't Hoff factor just a little bit above 1, but will not quite be strong enough to reach 2. We'll go over how to find that for this particular problem in a moment. Before we do that, let's quickly review the other symbols. Kf is called the freezing point depression constant. This will almost always be given to you directly, or you'll be given a table in which you can look it up for pretty much every instance in this class. Lowercase m, if you've watched the previous videos, you'll know that stands for molality. And the definition of molality is moles of solute divided by the kilograms of solvent. Now that we know the meaning of each of the symbol, we can figure out how many of these symbols we know and place them into the equation. Let's remind ourselves that the freezing temperature of the solution, which I've boxed in red, is our objective overall for this problem. I'll indicate that we definitely don't know that yet. Then the freezing temperature of the solvent, let's check the problem for that. You may be able to see at the end of line 2 that we have water for our solvent, and the freezing point of that solvent is exactly 0 degrees Celsius. We'll place a check mark next to the temperature of the solvent to show that we know this already. Next, we'll look to I and try to find the Van't Hoff factor. In line 1, it says that our solute is KCl. Now, KCl is an ionic compound that is very soluble, and so this will be an electrolyte. You may also be able to see that one of our ions in KCl will be potassium, K. The other will be Cl, giving us a total of 2 ions, K and Cl. This means our Van't Hoff factor is 2, and so we know what I is. We also have the freezing point constant, Kf. That is 1.86. We'll write that down and check that off as well. Now the last letter we haven't talked about is the molality. You may notice in the question we do not have molality, but we do have a piece of information that may help us get to molality. We're given that the mass percent is 15%, so I'll indicate that we do not know molality, but we can use the mass percent to get there. Our plan will be to change that mass percent to molality. I'll circle the molality, put a question mark next to it to show that there's a way for us to get it, but we don't know it yet. Once we get the molality, we'll be able to find the freezing temperature of our solution. Now, our solution is 15% KCl. When we have percent, we can assume 100 grams because percent stands for per 100. So we will say that there are 100 grams of solution. 15 of those grams are KCl. And if we subtract, we'll get our grams of water. Again, we know this is water because the question says we have an aqueous salt solution. Aqueous meaning water. 100 minus 15 is 85 grams of water. Let's also remind ourselves that molality is equal to moles of solute over kilograms of solvent. So for part A, we'll find our moles of solute. For part B, we'll find our kilograms of solvent. So for part A, we'll start with our 15 grams of KCl and change this to moles. Multiply by a fraction with grams on the bottom, moles on the top. Now, the mass of KCl we can look up on the periodic table. K is going to be 39.1 grams per mole, and Cl will be 35.5. Cl will be 35.45 grams per mole. We'll get a total of 74.55 grams per mole. We'll place the 74.55 next to grams, and then place 1 next to moles, and we divide this in a calculator. We'll end up with 0.201 moles of KCl. For part B, we'll now get the kilograms of solvent. Now let's remind ourselves that our solvent was water, and we can begin with 85 grams of that. We'll now get out of grams, and now get into kilograms, because those are the units we want for our solvent. Now 1 kilogram is the same as 1,000 grams, and so now we'll get 0.085 kilograms of water. Using these amounts, we'll now find our molality. Now that we have the answers to part A and B, the answer to part A goes on top of the fraction. Answer from part B goes on the bottom of the fraction. Our moles were 0.201. Our kilograms were 0.085. We divide in a calculator. We get 2.37 molality for our answer. We'll now write that next to the molality here so we can keep track of that. Now that we have the molality, we can write our equation for freezing point of the solution. The freezing point of the solution equals the freezing point of the solvent minus I times K times the molality we just found. The freezing point of the solvent, water, was 0, minus I, which was 2, times K, which is 1.86, times molality, which is 2.37. We can input this into a calculator and get the freezing point for the whole solution. When you place this into the calculator, the freezing point of the solution will equal negative 8.81 degrees Celsius. Briefly, let's compare that to pure water. Pure water has a freezing point of 0, but by adding 15% mass of KCl, the freezing point drops down to negative 8.81. Thank you for watching. We'll see you again soon.